Students, so today we just have a simple lecture that we want to run through quickly. Alright, so we want to start to look at the Nernst equation and how this equation can be applied to electrochemical cells. Now, of course, in the real world, the majority of times reaction conditions will not be standard. That is, the temperature will not be 25 degrees Celsius and the pressure might not exactly be 1 bar. Also, your solutions might not necessarily be 1 molar solutions. And this makes sense because if you think about it, if you design a few electrochemical cells to connect to each other to form a car battery or batteries for your laptop or your cell phones, the temperature at which you're using the batteries might not be 25 degrees Celsius. The pressure on any given day might not exactly be 1 bar. So we have to have another way to estimate the potential of an electrochemical cell, separate and aside from E cathode minus E anode. Now, so we need to be able to do that. Now, Gibbs free energy, and we'll start from there, relates three thermodynamic properties of a system under investigation, right? So G, delta H, and S, which is the H is enthalpy, S is entropy, G is the symbol for Gibbs free energy. Now, so generally, delta G is equal to delta H minus T delta S. And that basically shows the relationship between delta G, delta H, and also delta S. Now, we can relate the free energy under standard and non-standard conditions by the relationship delta G is equal to delta G naught plus RT ln Q, where Q here is the reaction quotient. Delta G naught here is the standard free energy change, and delta G is the free energy change under non-standard conditions. Now, so delta G reaction gives a measure of the maximum work of a reaction. Basically, delta G tells you the energy in a system which is freely available to do work, or the maximum work that a system can do. All right, and so delta G is equal to W max, which is maximum work. Now, galvanic cells also do work, but this type of work is electrical work, and we can find a way to figure this out. Now, this work that the galvanic cell does is what we use to operate our cell phones, our laptops, and other handheld electrical devices. Now, delta G is equal to minus NFE, where N is the number of moles of electrons, F is the Faraday's constant, and E is the potential. Now, what we could do is to substitute wherever there is delta G, we can replace that with minus NFE. Put right there and also right there. If we do that, then we'll end up with this equation here. Okay? Now, remember what quotient is. If you have a reaction, such as this one, then the quotient works out to be this. It's products over reactants raised to their coefficients. So for example, P2, right? P2 is raised to the third power, right? R2 is raised to the second power, right? Raised to 2, right? So that's how you calculate the quotient. It's products over reactants raised to their coefficients. Just a reminder. Right? Now, if we divide through, if in this equation we should divide through by minus NFE, right? If we should divide through by minus NFE, then we'll end up with this equation here. This is the Nernst equation. Okay, this is what we call the Nernst equation. All right, so as you have seen, hopefully a simple measurable parameter, E cell, can give many thermodynamic information. So we can get a lot of thermodynamic information by just measuring the cell potential. All right. Now, we could modify the Nernst equation a little bit by using, instead of ln, right? Instead of ln, we could use log. So we could do a little conversion. Remember, ln x is equal to 2.303 log x. And so here's the conversion. We are now switching from natural log to log base 10. And that's how we have this 2.303 RT over NF log Q. Now, if the temperature is 25 degrees Celsius, which is about 298.15, well, we have 298 here, then we could basically simplify this equation. We could work out all of this part, right? Because we know those numbers. So if the temperature is 25 and we know the universal gas constant R, and F is a constant, Faraday is constant, then we could basically simplify the equation and we end up with this one here. Okay? And so this is a simplified version of the Nernst equation. Okay? Right. At equilibrium, point out at equilibrium, where Q is equal to K, note that the cell does not produce potential. So the potential coming out of the cell is zero. Of course, the cell still has standard potential. We'll always have that. But at equilibrium, then you find that there's no potential coming out. The cell has no potential. Right? And that's something to know. So when you have your cell phone and you say that, okay, your cell phone is dead, it means that the battery, the cells that make up the battery are at equilibrium. And so what you have to do is to recharge those cells, basically pushing them away from equilibrium. Okay. Now look at this. Look at this galvanic cell here. All right, and we want to apply the Nernst to it. One side of it, as you can see, is the She, right? Standard hydrogen electrode. Whereas the other side is a cadmium salt cell. Okay. The overall cell reaction is given to us, here it is, and the standard cell potential is given to us as 0.4 volts. We're going to use the Nernst. First thing we could do is to calculate Q, which is the reaction quotient. Okay, products, the products that we have are cadmium 2 plus and hydrogen gas. Okay, and so which products over reactants? So it's cadmium 2 plus. The pressure, well, the concentration of a gas is basically the same thing as its partial pressure. So what I could do, instead of writing square brackets there, what I could do is just write partial pressure hydrogen gas. Okay, that's what I could do. The reactants now, cadmium solid, a pure the concentration of a pure solid is 1. All right. For the H plus concentration, I don't need to put the concentration of the cadmium solid. That's 1 squared. Some persons will tell you that, which is actually accurate, that the activity of a pure solid is 1, and so you don't need to put that. So here we have our quotient. This is Q, and it is what is written here. All right, if you study what is here, okay, you put the values in, and so you get a Q of 0.010. Right, that's Q. Now you can just substitute that into the Nernst. Okay, we put the standard cell potential here. Yes, we have this part which is from the Nernst. We have 2 electrons. There's a 2-electron process, right, to convert cadmium 0 to cadmium 2 plus. All right, and put our Q, and we take the log of that, and the voltage is, the cell potential is 0.46 volts. Okay, that's how you use the Nernst equation. Here is an example that you can try. You can go ahead and try that example. Okay, now I want to discuss quickly qualitatively corrosion. Now, corrosion is an electrochemical process. It's a redox process, reduction oxidation process. Okay, and it's quite important. It's quite important. Let's look at, for example, the oxidation of iron. All right, which is what that process is called rusting. And let's say we're looking at it in a slightly acidic media, aerated, meaning that we have air, aqueous media. So you have, for example, a droplet of water on the surface of a piece of iron, and a number of reactions take place. For example, one part of the at one part of the iron there will be oxidation of the metal from iron 0 to iron 2 plus. That's that part of the metal must be the anodic part. And then at another part you'll have reduction of oxygen. Let me show you this in simpler form. So overall, what you will have is iron getting converted to iron 2, right? So iron 0 getting oxidized to iron 2. This is ox. Whereas you have oxygen moving from oxygen 0, right, to oxide. This is red. So we have red ox. All right, red ox. Okay, that's why corrosion is a redox process. At the anodic, as I was saying earlier, at the anodic region of the metal, you have iron 0 being converted to iron 2. That is oxidation. And we know that oxidation occurs at the anode. So wherever on the metal or whatever region of the metal this is occurring, this is the anodic process. We also have the cathodic. We also have cathodic process occurring where oxygen is being reduced to oxide. Okay? Yes, hydrogen oxide, oxide, water is an oxide. Okay? And so when we can look further at what happens to the iron 2. The iron 2 is further oxidized, all right, to iron 3. That's another redox process. Okay, because the oxygen is also reduced here to oxide again. After we have formed iron 3, then the iron 3 could react with water to form iron 3 oxide in the hydrated form. And that is what you call rust, like red brown substance. Okay, now that is very, very important because, and this is just a nicer version of the diagram. Yeah, it's a better looking version, I guess. It's colorful. You should note that this reaction can occur spontaneously, even under neutral or basic conditions. Okay, but of course, we have slightly different mechanism, but the outcome will be the same. Okay, yes. And as I explained earlier, electrons are supplied at the cathodic region, right? Yes. And of course, the anodic region is where we have oxidation. So, now, the whole idea of corrosion is a multi-trillion-dollar business. Why is that? Well, about 95% of all commercial goods are transported via the sea, right? Via the ocean. So shipping becomes highly important. Ships are made of metal. And if you have ships rusting away quickly, then you see the problem. So these reactions are multi-trillion-dollar reactions. And any process that can lead to a slowing down of these reactions is very important. Not only that, we use metals for a lot of things. And if we can slow down the rate at which our metals get oxidized away, then um, it is clear that these reactions are highly important. Right? And that will be significant. For example, underground storage tanks, some of them are made of metal. Um, buildings contain metal, steel. Okay, and if you can slow down the rusting of these, that's a big deal, right? How can we minimize rusting then, since it's so important, critical? Now we can do cathodic protection, All right, and this is by we will protect a metal by connecting a second metal that is a sacrificial anode to it. All right, this part might sound a little bit tricky. Let me give a quick overview of this. If you have two metals, for example, aluminum, let's say aluminum, uh, aluminum 3 plus. All right, we know that the reduction potential of aluminum 3 plus, all right, is something like about minus 1.66 volts. However, for zinc, all right, zinc 2 plus, the reduction potential for zinc 2 plus is something like about 0 minus 0.76 volts. Okay, now if you are supposed to, if you are trying to arrange an electrochemical cell using these two metals, zinc and aluminum, I am saying to you that the anode, the aluminum would be the anode. The aluminum would undergo oxidation, whereas the zinc will undergo reduction. In other words, the zinc would form the cathode, aluminum would form the anode. In other words, if these two metals are competing for being oxidized, the aluminum will be oxidized, right? Before the zinc will ever get a chance to be oxidized. In other words, if we have these two metals, right? Zinc and we have aluminum. If we connect the two of them via a piece of wire and they are in a solution, let's say they are in the soil, and of course there's some water in the soil. If this one is your tank, your storage tank, the aluminum would get oxidized before the tank gets oxidized because the aluminum is more reactive, right? And it would rather to undergo oxidation way more than the zinc would rather to undergo oxidation. In other words, the oxidation of aluminum is more spontaneous compared to that of zinc. So the aluminum metal will get oxidized away before the zinc metal, therefore reducing or slowing down or preventing for a long time the oxidation of your zinc tank. All right. So the aluminum was used as a sacrificial anode. This is what we call cathodic protection. Okay. Okay. That's critical. And as you can imagine, there are other ways to mitigate or to fight against oxidation of your metal or corrosion. You could use coating. You could try to do coating. Like for example, you could paint your metal with a polymer or so to prevent oxygen accessing the surface of the metal. You could also galvanize your metal. So if you have iron, just cover the surface of it with a piece of zinc, a thin layer of zinc. But of course, that will serve two purposes. The zinc will be sacrificially oxidized, but once that gets broken, then your iron is exposed. However, nonetheless, the zinc will be there for a while to protect the surface of your metal. But after a time, you have to understand that you'll lose your metal. Okay? So you could do the galvanization of your metal, or you could do coating. These are really viable ways that can be used. Okay, and this is a diagram of the tank being protected by a piece of aluminum metal. All right, and you can imagine that even, for example, something like an oil rig, which is out there standing in the ocean, would need some sort of protection by some method or the other. Okay, guys, that is it. As I promised, it would be a simple lecture. Okay, so that is that for that lecture that we missed.